So Newton used gravity to understand tides. Humans were traveling all over the world by the 1600s. Columbus sailed in 1492. By the time Newton was around in the late 1600s, that was almost 200 years ago. So for him, so we were traveling all over the world. Most people lived near coasts, and people understood tides very well. They knew tables of them. They knew that the time between a high tide and a low tide was a little over 6 hours. They knew that there were these things called spring tides, which happened every few weeks, and neap tides, which were happened every few weeks and alternated between the spring tides. And they didn't understand. They didn't have a good physical explanation for why they happened or what they were. But they knew spring tides would be really big high tides and really low tides, and neap tides, the highs and the lows wouldn't be as far apart. They knew it was correlated with the moon. And so Newton, once he took his law of gravity, he began to, he was able to understand what tides were. And so here's an explanation of tides. This is any object, any large object like a planet or a star or a moon, anything like that. And I have three objects out here. 1, 2, 3. I'll number them. 1, 2, 3. I don't know if you can even see that. They can be billiard balls or marbles or anything large, as long as they're not as big as this, or as long as they're very small compared to this. These could be boulders or something. And so I'm going to ask you, which of these experiences the greatest gravitational force due to this guy, or are they the same? So if you remember, the force of gravity is G times the mass of one object times the mass of the other object over the distance between them squared, right? And so if I wanted to look at the force of gravity on object 1, right, I'll say, I'll just call that an M there. So maybe big M and little m. And then I can say, look, that's G times this object, which we'll call M, times M1 over R1 squared. Well, if they all have the same mass, if M1 and M2 and M3 have all the same mass, then I can just leave it like that, right? But they have different R's because this is R1 from the center, that's R1, and this is R2, and from the center here out to there is R3. And you can see the force of gravity on 3 is going to be smaller than the force of gravity on 2 because it's going to have a bigger denominator. So if these guys all three have the same mass, this guy experiences the strongest force, this guy next strongest, and this guy next strongest. And so if I drew little vectors for their forces, I would draw a longer vector, right? We call this F1. I'll draw a smaller vector. That's F2. That's the force on 2. And this is F3. So the strongest force is on the object that's closest to the moon or the planet, and the weakest force is on the one that's farthest away. And the effect that has is to pull these things apart. It's called a tidal force, and it pulls on the nearest one stronger than it pulls on the farthest one. It has a lot of interesting implications in astronomy. If a smaller object gets too near a bigger object, the bigger object will rip the smaller object apart. And so if we redraw this picture and say this is the moon here, and say this is
may be beyond my.
And this is the Earth. They do this to each other. But we're just going to look at the effect of the moon on the Earth. I'm going to draw a little further away. This is, again, not a scale drawing. And so we're going to pretend here that the Earth is completely covered with water. And so I'll just, we have oceans that cover about 70% of the Earth. But let's just pretend that the Earth is all water, right? Well, now, the moon is pulling harder on this water than it is on this water. And so the oceans, water gets pulled towards the front, This is a huge exaggeration, right? And then it left behind in the back. And so rather than having a circle, you end up with something like that looks like this. It's bulged along the direction of the moon, and it's flattened in the areas perpendicular. And so if I make a comical version of me, if this is me standing, right, in each of these places, right, I have a high tides here and here, that is to say along the line connecting the Earth and the Moon, and I have low tides here and here perpendicular to that line. Because this water's getting pulled the hardest, gets pulled ahead. This water's getting pulled the weakest, it gets left behind. By the way, this effect also happens to the Earth, but it's much more solid and it doesn't move around as easily, and so it's mostly the water that gets affected by it. So now the Earth is spinning, right? And it takes 24 hours for it to go around once. And so in a typical day, can you tell me what time of day? Oh, never mind, the sun isn't in this picture. In a 24-hour period, the Earth would rotate one complete cycle, and it would go from high tide to low tide to high tide to low tide to high tide again, right? And that would be one complete day. And so that's almost what we see when we look at tides. They actually take a little more than 6 hours to go from a high tide to a low tide, and then 6 hours to go, a little more than 6 hours. And so I'm going to show you why in the next drawing. So if I put tides on here again. And so now here's the moon. So let me draw the Earth. Here's the Earth, right? And here's the moon's position here. There's the moon, right? And so I'm going to draw that crazy looking tide thing here. So here's the ocean's bulging here and bulging back here, right, like that. So I have a high, a low, a high, and a low. And so over the course of 24 hours, you experience 2 highs and 2 lows. The catch is, after 24 hours, the moon isn't here anymore. It's over to here now, because the moon is orbiting the Earth once every 27 days, and so the moon has moved a 27th of an orbit every day, which is about 12 degrees or something like that. And so now my moon is over here, and so I'm not getting back to here to get to my next high tide. I'm getting back to here, getting to here to my next high tide. And so over the course of 24 hours, I won't get 2 high tides and 2 low tides. I'll get a little less than that. Every high tide, tomorrow's high tide at the corresponding time would be a little later than 24 hours later. And so it's 6 hours and something number of minutes between a high and a low and a low and a high and a high and a low and a low and a high. And so that's the sort of the basic explanation of tides. And now I'm going to show you what effect the sun has on that. So now I'm going to make this drawing even more complicated. I'm going to draw sun over here. Again, I should just have this, little warning. The sun's diameter is 100 times the Earth's diameter, and the Earth's diameter is 4 times the moon's diameter. So we couldn't do a scale drawing on here very well. And so we're going to say, look, here's the sun. I'll draw the Earth over here, say. There's the Earth, and I know the Earth is way too big for this scale, and now I'm going to draw a little. Here's the moon's orbit, right? And so the sun.
the sun produces about half the tidal effect that the moon does. And the sun is much more massive than the moon. The sun is 300,000 times the mass of the Earth, and so that means it's about 300 million times the mass of the moon or something like that. But the sun is much, 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 much farther away. And so it's actually the moon that has a bigger tide effect on the Earth. And so if this is the moon, then when the sun and the moon and the Earth make a line, then both the sun and the moon are stretching the Earth in the same direction, whether they're on the same side or on the same side of the Earth together or on opposite sides of the Earth. When the sun, the moon, and the Earth make a line, the tides are a little bit bigger than normal. When the sun and the moon and the Earth are at 90 degrees in these two positions, when the moon is like this, so the moon's trying to stretch the Earth this way, but the sun with its weaker effect is trying to stretch the Earth this way, tides are smaller. And so these two positions give neap tides, and these two positions give what's called spring tides. And so I'll write a little definition of those. So spring tides, they're called spring tides, not because they happen in the spring, nothing to do with the spring. It has to do with the fact that they spring up. When the moon moves into this position or into this position, you suddenly get these extra large tides on the Earth when they get lined up. And so spring tides occur when the sun, the moon, and the Earth make a line. So these positions or these positions, either one will give a spring tide. Extra high tides, extra low lows. Neap tides try one more time. Neap tides occur when the sun, moon, and Earth make a 90-degree angle. And this gives these give low high tides because the moon's stretching the Earth this way. It's from these two positions. So the moon's stretching the Earth this way, and the sun's stretching a little bit less this way. And so the sun is just kind of reducing the effect the moon has. Or when, on a high, if you're in the high tide position, you get a lower high tide. If you're in the low tide position, you get a higher low tide.